Here, we are going to draw a plot in which we will represent free electron and hole concentration in n-type and p-type region. In the p-type region, far away from the junction, obviously hole concentration is greater than free electron concentration. And as we move towards the junction, the hole concentration will start to decrease as the holes have moved to the n-type region due to diffusion. So, the complete plot of hole concentration will look like this. Similarly, we can plot the free electron concentration. The region between the two red dashed lines represents the depletion region, as theoretically this is the region which is devoid of charge carriers. Now we will plot another diagram representing ionized doping concentration in n-type and p-type region. We will draw a single curve ND plus minus Na minus. Nd plus represents the ionized donor impurities, whereas Na minus represents the ionized acceptor impurities. We will take 0 on the y-axis here, and after that we will draw the plot. The plot of Nd plus minus Na minus will come out like this. The straight line on the y-axis representing nothing but the metallurgical junction. In the p-type region, the area which is negative represents Na minus, which further represents the negative charge present in the p-type depletion region. Similarly, this area represents positive charge present in the n side of the depletion region. In this diagram, you can see that the shape is irregular, making it difficult to calculate the area under Na minus and Nd plus, which actually represents the total positive and negative charge in n-type and p-type region. This area is used in further calculations to derive many important formulas. So, we use depletion approximation, in which we extend the straight line slightly to give Nd plus minus Na minus curve a shape which looks like a pulse, but still covering approximately the same area. We actually assume that in the depletion region, all the dopant atoms are ionized, meaning that Nd plus is actually equal to Nd and Na minus is equal to Na. When we consider the depletion layer approximation, the length of the depletion width actually decreases, as this area represents the total charge in the depletion width. And for maintaining the same charge in the depletion region, the depletion width reduces slightly after considering the depletion layer approximation. Like any other approximation which you have studied in this subject, this approximation also aims to make mathematical calculations easier. For example, even though in one side of the semiconductor device there is positive charge and on the other side there is negative charge, but still the semiconductor as a whole is neutral, meaning that negative charge in the p-type region is equal to positive charge in the n-type region, and we can find the negative charge to be equal to ionized acceptor impurity concentration multiplied by volume of the depletion region in the p-type region. Similarly, we can find the positive charge to be equal to ionized doping concentration multiplied by volume of the depletion region in the n side. In the graph, you can see that this is depletion width. Now let us assume that this is Xp, which is the part of the depletion width in the p-type region, and this is Xn, which is the part of the depletion width in the n-type region. We can write W is equal to Xn plus Xp. Now we will assume that the cross-sectional area of the semiconductor is A. We just assumed that all the dopants are ionized in the depletion region. Therefore, Na minus will be equal to Na and Nd plus equal to Nd. Volume in the p-type region will be equal to Xp into A. Similarly, volume in the n-type region will be equal to Xn multiplied by A. This A will cancel, which will give us a very simple yet very important relation, which is NA into XB is equal to ND multiplied by XN. Interestingly, depletion approximation is used to calculate charge in depletion region and electric field, but it is not used for calculating current as it would give infinite current. We know that diffusion current is equal to area multiplied by charge multiplied by diffusion constant multiplied by concentration gradient. If we have considered depletion approximation, then you can see that the concentration gradient at the boundary of the depletion width would come infinite, which is obviously not possible. You can actually destroy all the power generating industries if you somehow create a semiconductor device delivering infinite current. This is not possible. That's why we do not use depletion approximation to calculate current passing through the depletion region. I have attached the short notes for this chapter in video's description, which you must go through because it contains many small points which are important and can be easily understood. For example, the PN junction is having a symbol like this. This represents the P side and this represents the N side. There is nothing much for me to describe about this. This is just a symbol where you should know. Another important point is we never consider that the semiconductor is degenerately doped. We always consider the semiconductor to be non-degenerately doped. In our lecture, we have approximated the graph to look like a pulse, which is referred as step-graded junction. However, we can approximate it in other shapes like linearly graded junction as well. In most of the standard books, you are going to learn the formulas based on step-graded junction, but for having a clear understanding of the derivation, few authors have derived the formulas for linearly graded junctions also. It is very important for you to remember the formulas for step-graded junction as well as to understand every derivation carefully, as in exams, not only step-graded junction or linear graded junction, any other equation can be provided to you and subsequent formulas can be asked.